In this video, we're going to be talking about the quantum numbers, and the quantum numbers are actually used to give a detailed address of an electron or the location of the electron in a particular atom. So, we have so many electrons in those shells around the nucleus in a given atom. So how can you give each electron a unique address? And that's what comes from the quantum numbers. So there are actually four quantum numbers, and the successive quantum numbers are usually dependent on the previous one. So we're going to start out with the first one, and it's called a principal quantum number. The symbol for the principal quantum number is going to be n, and it actually gives you the information about the energy shells or the energy levels. So remember, you have these well-defined energy shells around the nucleus, and those information is actually given by the principal quantum number. So the values for the n could be 1, 2, 3, 4, 5, and it can go all the way to the infinity. Hypothetically, it doesn't really go in the periodic table, it doesn't really go to infinity, but when it does goes to the infinity, it just means the electron is kind of gone away from the perimeter of the atom. Now, and when you look at around the nucleus, so let's say this central dot is the nucleus. So the first shell is going to have the n value of 1, the second shell is going to have an n value of 2, and the third shell is going to have an n value of 3, and it just goes on around the nucleus. Now, what do they really represent in the periodic table? So if I go back and, if I look at the periodic table, you have the periods and the groups in the periodic table. This principal quantum number, the energy shells, actually represents periods in the periodic tables. So if you recall, the periods are your horizontal rows in the periodic table. Okay, so once you know about the principal quantum number, like let's say if I have an electron that's residing in the third shell, now this third shell could be very big, and you have to have a little bit more information on where exactly on the third shell this particular electron lives. Okay, and that's when you have the second quantum number steps in, and the second quantum number is actually dependent on the first quantum number. So the second quantum number is called the angular quantum number. The symbol for angular quantum number is going to be L, lowercase l, and it gives information about the subshell or the sublevels inside the shell. So once you know your electron is in particular shell, your next job is going to be to figure out in which particular subshell your electron is going to be. Okay, so the value of L is going to be actually be 0, 1, 2, 3, all the way, and has to be at least 1 less than the value of n. So this is very important to know. Your value of n and the value of L cannot be the same. All right, the L value must be less than the value of n. So for example, if my n is 4, then the possible L values could be 0, 1, 2, and 3. It cannot be 4, and it cannot be more than 4. So that's the most important thing in here. If suppose my value of n is 1, then the value of L is only going to be 0. I cannot have 1 for the value of L, and I cannot have more than 1 for the value of L in this particular case. Okay, so in addition to knowing this relation with the n value, you also want to know what do we mean when we're talking about the subshell. So there are actually four subshells that we're really going to be focusing on here. And the first one is called an S subshell, and then you have P subshell, and you have a D subshell, and then you have the F subshell. And if you actually go back and look at your periodic table and see what that really familiar to, these are actually your blocks in the periodic tables. Remember, you have S block, P block, D block, and F block in the periodic table. This is where these blocks are actually coming from. So when you have S subshell, or when your electron is in S subshell, your L value is going to be 0. Okay, when you are in P subshell, your L value is going to be 1. When you are in D subshell, your L value is going to be 2. And when you're F subshell, your value is going to be 3. So make sure you have these values memorized in order to figure out your subshells. Okay, so let's look at a question here. So suppose I have an electron that's in 4s subshell. Okay, so if this is in 4s subshell, my job is to figure out what the n value is going to be, and my job is going to be to figure out what the L value is going to be. So the n value is always going to be represented by which number you have in the front. So in this case, you have 4. So the value of n is going to be 4. Then what's the value of L going to be? Now, recall if your value of n is 4, the possible L values could be 0, 1, 2, 3. Now, you're not going to have all of those values at a given time. You may have only one at a given time, and that's determined by what particular subshell you are in. So in this particular case, you are in S subshell, so that means the L value is going to be 0. So as long as your L value is going to be less than the N value, your subshell is going to be valid. So a particular question sometimes they ask you is which shell is valid and which shell is not valid. So let me take another example here. What if I have maybe 3D here, 3D subshell? Now let's go ahead and figure out what the n value is going to be. So the n for 3D is going to be 3, and the L is going to be, if we go back here, when the subshell is D, the n value is 2. So that's why you have to memorize these values. It's going to be 2. And L value right now is less than the value of n. So that means it's going to be a valid subshell. Okay, maybe take another example. What if I have something like 3F. So if I have a 3F subshell, what's the n value going to be? Well, the n value is 3, and what's the L value going to be? For F subshell, the L value is also 3. So now this L is not less than the value of n, so that means this particular subshell is actually going to be invalid. So that's how you figure out if the subshell is going to be valid or invalid. Like what if you have something like 1D? So in 1D, the n is going to be 1 and L is going to be, well, go back and look what the value going to be for L when you're in D subshell, it's 2. So again, the L is not less than the value of n, so that means this is going to be invalid as well. Okay, so make sure you know how you actually figure out if your subshell is going to be valid or invalid. Okay, now you know which particular subshell your electron's going to be in. Now your subshells could also be fairly big. As the numbers goes up for the value of L, the size of the subshell obviously goes up as well. So when you're looking at the next quantum number, it talks about the electron, about the information about the orbitals that's going to be inside the subshells. Okay, so symbol for the magnetic quantum number is going to be m of L, and the value of m of L is going to be going from minus L, passing through 0, and going all the way to the positive L. So for example, if my L is 0, then the m of L value is going to be just 0, because writing minus 0 and plus 0 doesn't really make any difference. And then however many values you get for the m of L, that will tell you how many orbitals you're going to have in that particular subshell. Okay, so if it's 0 for m of L, you're going to have only one orbital in that particular subshell. What about if you have a value of L to be 1? So when the value of L is 1, you are in P subshell. So it's going to be minus 1, 0, and plus 1. Okay, so then you have 3 values in there. So that means there's 3 orbitals in P subshell. So that's the information you get in here. Moving along, if the value of L is 2, which means you're in D subshell, then it's gonna be minus 2, minus 1, 0, plus 1, plus 2. So that actually gives you 5 values, so that means you're gonna have 5 orbitals in the d subshell. And then the next one you have to worry about is when the L value is 3, which means you're in F subshell. And when you're in the F subshell, it's going to be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So you have actually 7 orbitals in there. So the way it goes up, it goes by 1, 3, 5, 7, a number of orbitals in the particular subshells. Now, other thing you want to know is the max electrons that can be placed in an orbital would be 2. Okay, so if you can place 2 electrons maximum in a particular orbital, so how many maximum electrons you're going to have in this particular subshell? Let's say we're talking about the S subshell here. So let's say max electrons. So since you have only one orbital in there, it's going to have only 2 electrons in that particular subshell. Okay. When we look at P subshell, we know we have 3 orbitals in there. So how many maximum electrons are you going to have? Well, 6. If you have D subshell, in D subshell you have 5 orbitals, so it's going to have a maximum of 10 electrons. And in F subshell, you have a maximum of 7 orbitals, so that gives you a maximum of 14 electrons. So you may want to look what these numbers are familiar to in the periodic table. So you got 2, 6, 10, and 14. So if you go back and look in the periodic table, and if you look at your blocks, so how many groups you have in S block? Well, you got 2 groups in S block. You have 6 groups in P blocks, and you have 10 groups in D block, and you have 14 groups in F block. So these numbers actually also represents the number of groups in a particular block in the periodic table. Alright, so make sure you are able to figure out the number of orbitals, the number of electrons in a given subshell. Okay, so once you have this much information, you can talk about this last quantum number, which literally just depends on the orbitals. It's called a spin quantum number. So it says the spin of the electrons in the given orbital. So far we have the information up to the orbitals. And now how the electron is going to be placed in an orbital. So remember what we said, we can place a maximum of 2 electrons in a given orbital. So suppose I have this orbital right there. So in this particular orbital, since I'm placing 2 electrons, I'm going to be placing those with an opposite spin, which means if one electron points up, the other one points down. So that means the values of S of L is going to be either plus half or a negative half. Okay, so those are the only 2 possible values you have for a particular spin quantum number. Okay, so you have multiple values possible for the magnetic quantum numbers. So they are going to be obviously dependent on your angular quantum number. And then your angular quantum number is obviously going to be dependent on your principal quantum number. Okay, so let's look at maybe this question right there. So this question actually talks about all 4 quantum numbers. So suppose this is n on the first column is n. This is actually going to be L, so it doesn't really take that as an L, but suppose this is L values, and then you have M of L and you get the S of L. So let's see if those particular numbers are valid or not. So let's suppose look at the first one. So your n is 5. Okay, so if your n is 5, what are the possible values for L? So remember, it could be 0, 1, 2, 3, 4. As long as it's less than the n value, that's all that really matters. Now, you're not going to have all of them, so even if you have one of them in there, that means it's fine. So you have the L value to be 2, so that means that's good. Okay. Now, once you have the L value, your M of L value is actually going to be dependent on the L value, which would have been minus 2, minus 1, 0, plus 1, and plus 2. So now again, you're not going to be given all the values. You may be just given one value, and as long as that particular value falls in the range of these given or possible values, that's all it really matters. So this m of n is going to be -1, so that's fine as well. And this s of L is either going to be positive half and negative half, and that's all really going to be looking for. So this one seems like it's valid. Okay, let's look at maybe the next one. Your n value is 1, so the only possible value for L is going to be 0, so that's fine as well. So if your L is 0, the only possible value for m of L is going to be 0 as well, because -0 plus 0 doesn't really make any sense. And then your S value is going to be, well, it could be either positive half or negative half. So if you have any one of those, is fine. So that one looks fine as well. So that's a valid quantum numbers as well. Let's look at C here. Your n value is 3, and your L value is also 3. Okay, so that's a little bit fishy right there, because what we know so far about the quantum numbers, your L value must be less than the value of n. So as a result, this is going to be an invalid quantum numbers. Okay, so the last one here, the n is 5, your L is 3. That's fine, because as long as it's less than the 5, that's all that really matters. And the possible values for m of L here is going to be -3, -2, -1, 0, +1, +2, +3. So that's fine as well, because -2 is in the range here, so that works well. And your spin quantum number is going to be either positive half or negative half. So that really doesn't depend on the other values. As long as you see it's either positive half or negative half, that's all really matters. So this one seems fine as well. So it's going to be a valid subshell as well. Okay. All right, so this is how you're going to be looking at the quantum numbers, and I have some more videos posted where actually I have done the practice problem just looking at the quantum numbers. If you have any questions, feel free to leave the comments in the section below.